Okay, hello everyone. So in this video, it's gonna be the conclusion of the chapter 5. Okay, the special description. We have another chapter to go, chapter 6. But chapter 6 is a very short chapter. Okay, and this one we talk about the multinomial distribution and variant normal distribution. After lesson 40, we have lesson 41, right? So lesson 41 is a surprise. Okay, so normally for chapter 1 and 4, when we finish the content, so this lesson is the last lesson for the content, right? But if we finish this chapter, we are not going to look at the exam strategy, neither the big picture, but in the next video, it's gonna be the surprise. Okay, it's gonna be the surprise. So if you don't want to miss this video, please subscribe. Okay, please subscribe so that you will not miss the surprise. So the surprise is that we're not going to talk about the exam strategy. Neither do we talk about, let's say, some kind of the big picture or the exam. No. Okay, but this video, next video is gonna be fun. Okay, so I make sure that it's gonna be fun. Okay, so okay, coming back to our lesson, we are going to talk about the multinomial and variant normal. Okay, the multinomial, we have x1 up until xk. Okay, and with this kind of probability distribution, n of x1 up to xk. So if you look at this carefully, it is the generalization of the binomial distribution, right? Because if you have two distribution n, x1, x2, p1, x1, p2, x2, if x1 plus x2 equal to n, if you substitute this, it is binomial. But for the multinomial, we have many outcomes, right? We have many outcomes, and you can deal with that. And these are the property EXI. So very similar formula, right? NPI is NP. NP times 1 minus P is very similar. But look at this one. So the covariance between X and Xj is minus. What does it mean? It means that intuitively we have N fixed trial. We have N fixed trial, right? So if Xi occur too much, what does it mean? Because we have fixed trials, right? So Xi occurs then most of the time. So Xj, where j not equal to I, will reduce. The number of trials will reduce. So you can look at the formal proof in the textbook, but it's kind of the intuition to see why the covariance is negative. Okay. The next distribution that we are going to talk about is the bivariate normal. The bivariate normal, we have something like this. This kind of thing, I took it from the textbook. So the thing to notice is that we have kind of this parameter. Mu, mean of the first one, okay? Mu2, mean of the second one. Sigma 1, the standard deviation of the first one. Sigma 2, the standard deviation of the first two. But not only that, we have P also, rho, let's say rho. Rho is the correlation between x1 and x2. Okay? And this one is the formulation. It look a little bit similar, right? 2 pi times something like this. So it's very similar to the variance. And this one very similar to the variance here. And x1 minus mu is very similar looking. Okay? However, you could notice that even though we talk about two variables, it is like a mess because we have to cram all these into one slide. But how about if we want to talk about in the 3, 4, or 5 or n variables, a mess or impossible, right? So usually when we talk about more than one variable, normal distribution, let's say bivariate or the multivariate, we talk about it in terms of the vector, okay, in terms of the matrices, because in terms of the matrices here, remember, if it's one variable, what happened? 1 over square root 2 pi sigma, let's say sigma square root exponential of minus 1/2 x minus mu x minus mu over sigma square, right? So it is very similar looking, but this one, instead of 1, we have n variables, right? It is n over 2. And determinant of V, because when we talk about the variance, we talk about the variance covariance matrix, right? V is the variance and covariance matrix. And this one is going to be what? X minus mu. V inverse is 1 over sigma square, right? Times this one. So this one is the concise notation. So usually we will use this distribution when we talk about, let's say, when you study the mathematical statistics. Okay, but we are not going to go much into the detail here because we are in the probability theory class, right? Okay. And this one is a picture, okay? The scatter plot, okay? The scatter plot of with 25% of the rest of the ellipses, okay? So from this kind of the scatter diagram, you could see that, okay, this is spread, it is spread roughly equally, right? But you could notice here that it kind of move together, right? It's kind of like the rho is positive. So you can ask the further question. What if we know first Tata's joint? Can this help to predict the second Tata's joint? Right? Because we have some relationship between them. So in chapter 4, we talk about minimizing MSE. Right? So to predict this, if you want to minimizing the MSE, what should we do? We just use what? Use the conditional mean. And further, because this one you learn in the probability theory, right? But further, if you learn mathematical statistics, we can say that you could generalize this into the regression. Let's say the linear regression. Okay? So if we plot off this together, you could see that if there are some relationship between them, we could use one variable to predict the other one. Okay, and this is the techniques that the data scientists usually do when they first export the data to see the relationship between each pair of the variables. Okay, and this one, these are the properties. Okay, x2, the expression of x2 given. Okay, or let's say the first property first. For the normal, okay, usually in chapter 4, I have said that uncorrelated independence implies uncorrelated, but uncorrelated does not imply independence, right? But now if it is the normal, it can be. Because if uncorrelated doesn't mean rho equal to 0, it is easy, okay? Look at the formula. It is easy to separate this 2 or 3 terms into multiplication of each term. So for the normal only, okay, this is a very special case. If uncorrelated, it implies independence. And okay, this is the conditional mean, right? If we talk the conditional mean, it is very similar to the regression. So you could get this kind of formula here. And then if you talk about the conditional variance, this one is a formula. So intuitively, if rho is positive, that means in the last case, right, when x1 and x2 move together, if x1 increase, let's say rho is positive, e of x2 will increase too. Okay, and this one, if rho is very high, that means this one is very low. The whole term very low. That means predicting the two variables, predicting one variable using another variable, where the relationship is tightly close together, that reduces the conditional variance too. That means your forecast will be more precise. Okay, and these are the, let's say, the basic properties of the multinomial and variate normal. Okay, so in the next lesson, stay tuned for the surprise. And in the last few lessons, we are going to go to chapter 6. So see you.